In today's video, we'll explore a fundamental challenge in deep learning known as the vanishing gradient problem. This issue has been one of the major hurdles in training deep neural networks, and understanding it is essential for anyone working with machine learning. Before we dive into the vanishing gradient problem, let's quickly review how neural networks learn. Neural networks consist of layers of interconnected nodes, or neurons. During forward propagation, the input data passes through these layers, with each neuron applying a transformation to the data. This transformation typically includes a weighted sum followed by an activation function. The network produces an output, which is compared to the expected result to calculate the error. To improve the network's predictions, we use a process called backpropagation. First, we calculate the gradient of the error with respect to each weight in the network. Then, we update the weights in the direction that reduces the error. This calculation uses the chain rule of calculus, where gradients are multiplied as they flow backwards through the network. Now, let's explore the vanishing gradient problem. As neural networks get deeper with more layers, a significant issue emerges. Let's look at what happens with the traditional sigmoid activation function. The sigmoid function squashes input values to outputs between 0 and 1. If we look at its derivative, we'll notice it reaches its maximum of 0.25 at the center and gets smaller as we move away. When we backpropagate through multiple layers, these small derivatives are multiplied together. This repeated multiplication of values less than 1 causes the gradient to become exponentially smaller, effectively vanishing, as it moves backward through the network. As a result, the weights in the early layers receive minimal updates, making it difficult for deep networks to learn. So, how do we address the vanishing gradient problem? There are several effective solutions that have been developed. One of the most popular is using alternative activation functions like ReLU, the rectified linear unit. Unlike sigmoid, ReLU simply returns the input value if it's positive and 0 otherwise. Its derivative is either 0 or 1, which prevents the gradient from shrinking as it backpropagates through the network. Another approach is batch normalization, which normalizes the inputs to each layer, keeping the values in a range where activation functions work well. Skip connections or residual connections allow gradients to flow directly from later layers to earlier ones, bypassing the layers in between. For recurrent neural networks, architectures like LSTM, long short-term memory, were specifically designed to address the vanishing gradient problem through gate mechanisms. What does solving the vanishing gradient problem mean for deep learning? These solutions have been revolutionary for the field. They've enabled the training of much deeper networks, which can learn more complex patterns and representations. This has led to significant performance improvements across various tasks, including image recognition, natural language processing, and reinforcement learning. Many of the most innovative AI systems today, such as transformer models like GPT or deep convolutional networks, rely on these techniques to function effectively. To recap, the vanishing gradient problem occurs when gradients become too small as they backpropagate through deep networks. We can solve it using better activation functions like ReLU, implementing batch normalization, using skip connections, or with specialized architectures like LSTM. Understanding these concepts is essential for anyone working with deep neural networks, and they continue to be foundational for new innovations in AI.